Oh, you guys are so prompt and on time.
But the rule is 3 minutes before.
Oh, good Lord.
That's what I go by.
Yeah, well, that makes you a good and responsible student. Good and responsible Zoom person.
It's always different.
Uh-oh. Somebody was breaking up there. Was that you, Jim, or is it somebody else speaking?
I'm hanging in there, but I'm working on it.
Yeah. Okay, so we're done with homework 1, and we're going to do homework 2 today. So before we move on to homework 2, I just want to sort of ask, were there any questions about homework 1 or anything that has gone on in class before today's assignment? Is it all clear? In retrospect, there's nothing we need to sort of re-clarify. Cool. So this week's homework is going to be much more similar to the rest of the 9 weeks homework than the first one was. Week 1 was really about making sure you guys were comfortable with all the basic mathematic machinery that we will see over and over again, so that when you run into discomfort in the future, it can be over the genetics rather than over the underlying math. Hopefully we'll have now the underlying math tools well in hand and be able to struggle to get the genetics right rather than the other way around. Because this class is ultimately trying to teach you the genetics, not the math. And so it'll be, the homework will be much more like today. So there'll be and much like today's homework, there will be hopefully a significant number of problems that are not so challenging when you've read the material or understood the material. And there'll be a few problems that are considerably more challenging. And you will come to recognize which is which pretty quickly, I imagine. And sometimes the more challenging ones will get the best of you, and other times you will defeat the most challenging and you'll be proud. But it doesn't really matter either way. The notion is the homework is hopefully going to push you to learn all the concepts we can teach you. And if a couple of them were too hard to get the first time around, that'll be fine. We'll get it worked out. So, any broad questions with homework 2 before we start on just going by problem again? Okay, we are going to begin with Carmen in problem 1.
Let me pull it up. Oh, can you enable screen sharing?
Oh, every week, every class, somebody's going to tell me to do that before they even check, they're going to know I didn't do it. And it'll be like a magical prediction.
There you go. Okay, so the question asks, for a single locus in Hardy-Weinberg with 2 alleles, plot the frequency of allele A1, homozygotes as a function of P. So here's my graph.
That looks awfully good. Does anyone, the x-axis is labeled a little funny. You have a 0 on one side and a 1 on the, where's the 0 and where's the 1?
Oh, on opposite sides, yeah. Yeah.
All right, if we put the 0 into the origin, like she drew it, everything is perfect about that graph. Anybody have any questions? That is the picture you all should have gotten, more or less. And we move on to problem 2 with Kevin.
Yeah, so let's see, share my screen. I kind of put all my graphs on one graph.
Right.
So,
A bunch of you guys did that. It's very neat and cool looking when you do that. And it'll give whoever does problem 3 a big hint what the answer ought to look like.
yeah. Let's see if I can zoom in here. So I have the frequency of genotype on one side, and then the frequency of the A1 allele on the other axis. So it says for a single locus, for 2 alleles at A1, A2, plot the frequency of A2 homozygotes as a function of P equals the frequency of A1.
Yep.
So it's basically like a mirror version of that.
That is perfectly what it is.
Yep.
Anybody have any questions about that? Okay. Why don't you show me what since you already have it on the screen, show me what the heterozygotes are to.
Sure, why not? Yeah, so the heterozygotes are just a function that maximizes that 0.5 frequency.
You're giving away the next problem again.
Yeah. So
But it looks like that. Yeah.
Yeah.
Anybody have any questions about any of these 3 graphs? That one of them, looks like part of a parabola with a maximum at 0. The other looks like maybe part of a parabola with the maximum at 1. And the other looks maybe like some upside down kind of parabola type thing with a maximum somewhere in between. That might be a half that we will discuss over the next few problems. Everybody clear on this? Okay. So Kevin has showed us the picture and asserted that the maximum was at a half. Christopher, can you prove that the maximum is at a half for us?
Yeah, so I think you have to do a bit of calculus.
Yeah, just a hint.
And it's been a while since I've done any calculus, so I don't know if I did it right, but
That's
I think
okay.
that essentially, when you're looking for a maximum, you take the f prime of the formula and you set it to 0, and when you do that, you get 0.5.
That is exactly right. So you started out with a formula that the frequency of heterozygotes was equal to 2 times p times 1 minus p, or 2pq. And then you expanded that out and got minus 2p squared plus 2p. And you want to find the maximum of that function with respect to p. So you took its derivative with respect to p and got minus 4p plus 2. And then you set that equal to 0, and you solved for p and found that p was a half. Brilliant. Absolutely perfect. And the way you know whether or not this is a maximum or a minimum, if you'd wanted to know that, I mean, you can plot it as you've done here. It's just seeing this obviously a maximum. Or you could have taken its derivative one more time and gotten the derivative is minus 4 if you're taking one more derivative. And it turns out if the second derivative is negative at the point you're looking at, it's a maximum. And if the second derivative is positive at the point you're looking at, it is a minimum. But you've already drawn it, and you're pretty sure that's a maximum just from the picture.
Okay.
Any questions about this? That is probably the simplest and best way to prove that is a minimum or a maximum. There are probably other arguments you could have made by looking at the curve as you approach a half from both directions and showing that it's increasing in both directions. But those are all amount to the same thing, really, of taking its derivative at that point. Questions? Well, we're making good progress on this homework. Taylor, can you take problem? I guess we're on 6 now, I guess. Yeah, Taylor? Yeah.
Sure. Okay. So I wasn't too sure about this problem, but I'll just kind of go through where my mind was at with it. So we're asked why is 2pq sometimes referred to as the total variance in allele frequency. And so I started just trying calculating the variance of allele frequency. It got a little complicated, so I just kind of started thinking about it a little bit more theoretically. So if we're looking at a single locus in Hardy-Weinberg equilibrium, let's say it has two alleles, A1 and A2, and P is the frequency of the A1 allele. If we were to randomly pick an individual from the population, the number of copies of the A1 allele, we can think of as a binomial 2P random variable, and the variance of this random variable is 2PQ. Alternatively, I was thinking if we were to just randomly sample an allele, whether or not it is A1 can be thought of as a Bernoulli P random variable with variance P times Q. And similarly, if whether or not it's an A2 allele can be thought of as a Bernoulli Q random variable. So adding together both those variances is 2PQ.
Cool. That's the intuition. That the amount of variance in a person is something like 2PQ. You know, it's the variance due to random sampling of two alleles. You've got two alleles, each of them will give you something like a variance of PQ. You're walking that at some level, random sampling of a diploid is giving you a variance of 2PQ. And we will see when we do problem, when we get to homework 5-ish, maybe 4, maybe 6, we'll start doing occasionally partitioning of the variance in allele frequency. And we will inevitably end up with something like 2PQ on the bottom and something else on the top. Something that is, say, less than 2PQ as part of the variance in allele frequency that is due to, say, population substructure. And some of you, particularly who are going to be ecologists, will encounter notions of FST and things like that over the course of your career. And one way there are a lot of complicated ways of thinking of things like FST, but the simplest will be you have taken the allele frequency and partitioned the variance and ended up with part of the variance that is due to substructure and part of the variance that's due to something else. And that will be how you understand why you end up with a PQ on the bottom. Anyway, we'll get to that. But thanks, Burke. So Zhengji, how about number, what if we're at 7?
Okay, number 7.
Problem next.
Okay, so number 7 is asking us to show what are the expected frequencies for each of the genotypes, and in this case we have 4 alleles, each of them with frequency P1, P2, P3, and P4 respectively. So so I assume it was for a diploid organism, and
Yeah.
to do this problem we just have to do multinomial expansion. So basically the square of P1 plus P2 plus P3 plus P4, and if you expand this, then you can see each of the terms. So the expansion are just the sum of all these terms.
Yep. Yeah, that's it exactly. The intuition for why that is the right solution is, you know, you've got A1 genotype. What's the problem? What's that probability? P1 for the first allele, P2 for the second allele. They're independent. P1 squared. A2, P2 for the first allele, P2 for the second allele. That's squared. Got yourself a heterozygote like A2, A3. It's probability of hitting an A2 with the first allele, P2, and A3 with the second allele, P3, which could have gone the other way around. Could have been an A3 first, then an A2, which would have been a P3 times P2. But multiplication is commutative. You can sort of switch their order, and you get 2 P2, P3. I think everybody sort of understood that. Were there any questions about this problem?
So when I was thinking about this one, I was kind of maybe going a little bit further than where we are right now, but the idea of, I mean, these P values are going to get so small if you have many, many, many alleles, right?
Yes.
And which is sometimes the case. And like, I guess I'm trying to understand, like, technically you could have, you know, an unlimited amount of alleles, right? We just maybe don't know about them all.
Yep.
And so these P values would go to almost 0, right?
Good, very well.
So what, does this make sense still in that scenario?
Does
or-
an infinite allele model make sense? Yes. And in fact, an infinite allele model is, I don't think we're going to look much at it, but it is one of the so the sampling distribution from an infinite allele model is one of the contributions of population genetics to overall probability theory. The distribution of allele frequencies under the standard neutral infinite allele model is now referred to as a Ewens sampling distribution. It was derived by Warren Ewens in probably the late 60s, very early 70s. And it is one of the most common distributions in nature for for situations where you get continual input into a system and continual removal of things from a system. That I remember being a graduate student and watching an ecologist painfully try to work his way through the distribution of the number of different trees in a particular forest. And the way he set it up, it was instantly going to be a Ewens sampling distribution. But he didn't know that. And it got very, very painful. And he mostly worked it out in the end. And he was very proud. Got a Ewens sampling. Here's the paper. That idea that when you get sort of continual input and continual loss from a system, and most things end up being very rare, is a very well-defined notion with very well-defined properties. And the sampling property from a closed system of it has a name, and it's called the sampling distribution. I don't think we're going to run into it, but it turns out you can know everything there is to know about a Ewens sampling distribution with one parameter. It is fundamentally a one-parameter distribution, and that parameter we will call theta. And over the course of the next few weeks, we will see what we mean by that parameter. Other questions? All right. With the next problem, we have Michelle.
All right. So this problem is consider the usual parameterization of Hardy-Weinberg. Show that P is in fact the frequency of the A1 allele. So the frequency of the A1 allele is given by this formula.
Or at least the stuff on the right. And you're going to try to show that it's equal to that thing on the left.
Yeah.
Yep.
So I just expanded it, substituted in 1 minus P for Q. The terms canceled except for P, and so P equals P.
That is correct. I will show you guys one. Oops, what am I doing? Yes, I'm going to stop your share for 1 second. And I'm going to show you people a trick. Where's my homework? If I close my own homework, where is... What? I'm sorry. This is not giving me the option right now of sharing preview. That's really weird. Why is, oh, there it is. Okay, changed its mind now. All right, sorry. So I should be sharing my screen. Is that correct? You all can see it?
Yes.
I'm going to give you guys I tried to say this out loud in class last time, but the generalized party Weinberg can be rewritten with terms involving F and terms not involving F. So when you start with Gillespie's formula, 1 minus F P squared plus FP, that can be rewritten simply as P squared plus FPQ. The heterozygote can be written as 2PQ minus 2PQF, and the other homozygote can be written as Q squared plus FPQ. So the format of P squared plus FPQ, 2PQ minus 2PQF, and Q squared plus FPQ, keeping the frequencies in that format will dramatically simplify a lot of this algebra. So for the frequency of the A1 allele, if you have it in this format, you get the frequency of the A1 homozygote, P squared plus FPQ, and then 2PQ minus 2PQF times a half. So you end up with what looks like an FPQ and a minus FPQ immediately, which just simplifies down to P squared plus PQ. You pull out the P's and then it will just P. This is going to be the first example of the algebra gets easier when we keep it in this format. And although everything you did there was absolutely perfect, some of the other problems will become even more hideous unless you've done unless you've separated out the F terms. Not that it's wrong not to. It is perfectly correct to do it just that way. It's absolutely correct. It's just, it will sometimes be a little bit more painful. Linnea, you're up next.
Okay.
Yep, there we
I'm here. One second. Think of this one. Okay. So number
What's line?
oops,
Nine?
number 9, sorry. Okay, there we go. All right. Oh, okay. So yeah, this one pretty similar to last one, I thought. And if I had taken the F terms on their own, I think it'd probably be even simpler. But at this point, I just expanded out all of the multiplications and just canceled like terms, and there's only one thing that ends up, which is this one right here.
That is exactly the correct way to do that. That is totally the correct way to do it. And you just and literally the only thing that possibly goes wrong with this, and that goes wrong with it 100% of the time if you're me, is one of the signs goes funny. is you get the minus 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 thing going, and one of the signs is funny, and you end up with a a horrible mess rather than the beauty of one. When you separate out terms right away, you get something that goes away almost instantly. That's the homozygote, the heterozygote, the other homozygote. You end up with P squared plus 2PQ plus Q squared plus 2FPQ minus 2FPQ. They go away in the first term, and you just have P squared 2PQ Q squared, which is 1. It's almost a one-line simplification. So there you go. But there was absolutely nothing wrong with your approach, other than it is subject to getting it wrong when you are as uncareful as I am. Up next is Mitchell rather. God, is Mitchell with the next.
Is that 10?
Yep, I think so. Yep, definitely. The long one.
So I did not do it, I think, the correct way. I just was plugging numbers into the equation above. I didn't know you could set equations up and calculate it out, but what I found when I plugged stuff in is when F is less than 0, 2PQ can approach 1. And if it's 1, this term is eliminated because it's 1 minus 1, so that would be a 0. So I assumed that it could only be viable F values would be from -1 to 1.
Yeah, that is actually absolutely true. That F can never be smaller than -1, and F can never be bigger than 1. But it turns out that for most values of P, F cannot be -1. So you can sort of see that right away if you plug in, I don't know. Well, we'll get there. But most of the time, F is not capable of being equal to -1 unless P and Q are very precisely picked. Did anyone work through the? Does anyone have a work through of the bounds that they would like to share?
Like the inequalities.
Yeah, like all of them. Yeah, like all 6 bounds. And
Okie dokie.
you want to go for it?
Sure.
All right.
Great. Can you guys all see my homework now?
Yeah.
Okay. So for problem 10, I basically set up an inequality for each one of the genotype frequencies because that's kind of the main piece of information that the homework problem gives us, is that what allows those frequencies to be between 0 and 1. And so that's what I set those bounds at. Seeing that this is what I end up with, I decided to split each one of those inequalities into 2, an upper bound and a lower bound. That would allow me to kind of mess around with the algebra and get F alone on one side. So that's essentially what I did for each of these. I split it into the greater than or equal to 0 part and the less than or equal to 1 part. So as you can see, this is the 0 part and the 1 part. And then I found the upper and lower bound for each of those individual frequencies. And so I did that for the frequency of heterozygotes. And these were the bounds that I got. Did that for the frequency of homozygotes, again, the other one. And this is what I found, just simplifying. And then I set Q to be equal to 1 minus P. And I grouped them into this set of 3 lower bounds and 3 upper bounds. Where I ended up getting stuck was kind of determining which ones are the most ideal for which circumstances. What I kind of ended up doing was plugging in numbers. I plugged in like a half, and I plugged in a quarter and 3/4. And kind of what I noticed was that which bound is the lowest depends on the value of P to some extent, but that is kind of where I got stuck.
Yeah. So the upper bounds are much easier to state. So one of your upper bounds is 1. One of your upper bounds looks like 1 plus 1 over P. That's that top thing.
Right.
The other one looks like, oh my God, 1 minus P is the number Q. The number 2 is the number 1 plus 1. So what I have is 1 plus Q over Q. So that's the number 1 plus 1 over Q. So the top one looks like 1 plus 1 over P. The middle one is 1. The bottom one is 1 plus 1 over Q. So since P and Q are positive, 1 over P and 1 over Q is definitely a positive number. So I've got 1 plus something positive, 1, and 1 plus something positive. So the best possible upper bound is just 1. So that's straightforward. The other end is a little funkier. So that top bit looks like minus P over Q. That bottom bit is, since Q is 1 minus P, is minus Q over P. So we have the top and the bottom bounds are minus P over Q, and the bottom one is minus Q over P. So if P is bigger than a half, Q over P is going to be a number bigger than 1. If it's less than a half, it'll be a number less than 1. So when P is less than a half, minus P over Q is a better bound than minus Q over P. And when P is bigger than a half, minus Q over P is a better bound than minus P over Q. Now let's look at that middle thing. That's the way you've written it, looks very much like minus, this one might not be quite right, I think. I don't think we should get a bound of minus Q over 2P. Let's see where that came from. Do you mind scrolling up? I think there might be a tiny bit of algebra.
So that would be coming from here.
Yeah. So what do you got there? You've got, oh, well, that's okay. So just written that way, you've gotten 1 minus,
Oh.
that's 1, that's, yeah. So it's 1 minus 1 over 2PQ.
This is?
Yeah, so I put the 2PQ, that's minus 2PQ over minus 2PQ is the number 1. 1 over minus 2PQ is 1 over minus 2PQ. So I've got the number 1 minus 1 over 2PQ. 2PQ is always less than, 2PQ is always less than a half. We proved that up at the top. So you've got a number that is always more negative than minus 1. You've got 1 minus at least 2. So your bounds are minus P over Q, which will be less than minus 1 whenever P is less than a half. You've gotten 1 minus 1 over 2PQ, which is always bigger than minus 1. I mean, always more negative than minus 1, smaller. And 1 and minus Q over P, which is also closer to 0 than minus 1. It is bigger than minus 1 when Q is less than a half. Does that all make sense? So this bound is always worse than your other two. Or at least, yeah, let's put it this way. At P less than a half, it is worse than the P less than a half bound. And at P bigger than a half, it is less than the Q over P bound. I probably said that weird. But so your 3 best bounds are on one end, the number 1, and on the other end, minus P over Q or minus Q over P, depending on whether P is less than a half or bigger than a half.
Okay.
And that's just nothing but, sort of, working the logic there at the end. But the setup of the problem, the structure of the problem, the way to do it, exactly as you've done it. Perfect.
Okay.
Does that make sense to everybody?
Actually, can I add something?
Sure.
So
You saw
I'm just
some
going to share my
clever
screen.
geometric way of seeing this?
Well, I can see this. Instead of messing around with the inequalities, I could just make some plots and see what's going on. So, so the first one is for the homozygous. I think it was AA or BB or whatever. So this is for the homozygous, and and X, I replace P by X because that's how this program works.
Yeah.
And you can play around with F. So, and the idea is that you need this red line to be between 0 and 1, regardless of what X is. So when you play with F, you can see that, okay, this is working, but once you go beyond 2, then you have values of for the frequency of homozygous that is beyond 1. So that's not working. So the upper bound is going to be 2. And then similarly, you can play around and see that you can go to 0, but beyond 0, then the homozygous frequency is going to be negative. So that doesn't work. So for the homozygous, for the homozygous, the upper bound is 2 and the lower bound for F is 0. Similarly, for the other homozygous, just doing the same thing, you can play around with F and just see what the values are. So I also did the inequality, and I also did some reasoning to show that these are indeed the correct bounds. But graphically, if you just make a plot and just play around with F, you can see what's going on. And this is probably way faster to figure out what are the possible values that F can take on. So the final solution, I think it's 0 and 1. So 0 is just the regular Hardy-Weinberg, and 1 is when it's all homozygous.
That is certainly the absolute limits. For any particular values of P and Q, those the lower bound is not. When P is not equal to a half or 0 or 1, the minus side is not achievable. You can't get to -1. You can only get there at the bounds. But yeah, that's how you can see the absolute limits are -1 to 1.
Okay, so I have a quick question then. So, sorry, can you hear me?
Yep, go ahead.
Okay, good. Because I was getting a little confused on my homework too, where I came up with like a bound of 2, and that seemed weird to me, but the bound is really for the homozygous to be 2, like 2. So what we're looking, like you said, is for an absolute value of where all the constraints are met.
Yeah, there is no values of P and Q that will allow F to be 2. Because when F is 2, the heterozygote would be way outside that limit.
Gotcha.
There are very few values of P and Q that will allow F to be -1. There are some, but there are very, very few. It has to be equal to, it's P of a half. That's the only case where I think F can be as large as -1. But every other case, it's bound by -P or over Q or -Q over P. For
Gotcha.
the to stay in the range.
Cool.
No.
Yeah. And that makes sense too when I'm seeing this table right now where you have 0 falls within the range of 1 to 1 or -1 to 1. So it works out. Okay, that makes sense. Thank you.
Yes, and 0 is always possible. It's always possible to be in Hardy-Weinberg. And in fact, you should assume it always is. The vast majority of the time, the vast majority of things you see will be approximately in Hardy-Weinberg. Yeah, I see you've gotten the exact same inequalities I was suggesting. -P over Q and -Q over P. Although you've written them in a slightly different format. Other questions? Anyone else want to? All right. Up next with whatever problem is next is Marissa. Marissa with us? Let's see. Maybe she didn't make it today. Let's see. Perhaps she didn't make it today. Okay. Up next is Kiana again. Sorry.
Oh.
I haven't gone yet if that is anything. I don't know if Kiana, you were already on the list, but.
I don't mind, whatever works.
Go ahead.
Me?
No. Who wanted to volunteer for it? Who was saying that they wanted to go?
Brooke?
Brooke.
Oh, yeah. I don't know if I want to do 11, but I at least at least I'm okay walking through some of my thought process on it.
All right, go for it, Brooke.
I think I'm actually happier with 12, but anyway, we'll give 11 a shot
You
and learn
volunteer.
from my mistakes.
Yeah, there you
Learn from my mistakes. Okay. Let's go to okie dokie. I'm just going to scroll down. Whoop. Apologies while I move Zoom. Okay. Okay, so I got a little bit, I wasn't exactly sure minimizing, and this I think was part of my confusion with 10, but I can at least walk through the value that maximizes heterozygotes. And so, and then some of what I was thinking about when I was trying to figure out the minimum. So for the maximum, what I did was I knew that when the frequency of your heterozygosity is 1, that's the maximum that you can be. So your homozygous are 0, frequency of A is 1. So I set 1 to equal to the equation with the F value. So 2p, and that is 2p times q times 1 minus f. I replaced out q with 1 minus p so that I could have just 2 terms that I was working with. And I also knew from the previous homework that when you you can maximize when you're at the half value. So I plugged in 0.5 for p and reduced everything down to get 0.5 equals negative 0.5 times f, which then when you do the math goes to f being -1 at the maximum heterozygosity. And then I guess for the minimum value, what I was trying to do was you can have your minimum value for heterozygous really at 2 values of p. So either when p is 0 or p is 1. So I was trying to plug those values in the same way for what I was doing, but I got a little funky with the math. So you can see I plugged in 0 for p. That gives you a bound of 0. And then I had 2p, 2 minus 2p as my upper bound when I did out the math to plug in for 1, p equals 1. I don't know if this was really the best approach because then I ended up getting this sort of weird range. But I think learning from the previous one, yeah, I'm not actually sure where in my math I might have messed that one up.
So really for this problem, I was thinking about getting an answer in terms of p.
Oh, okay.
So it comes out almost the opposite of how you've done it. So when you want a minimum, the minimum number of heterozygotes is always 0. So if f is 1, doesn't matter what value of p is. F equals 1 will always minimize the number of heterozygotes no matter what. Because 1 minus 1 is 0, doesn't matter what p is. So the minimum heterozygotes is always 0, no matter what p is, and at that value, f is 1. Does that make sense?
Sorry, I was just writing. I think it does. I was just writing that note.
So on your minimize, you have 0 equals 2p q 1 minus f. If f is 1, that number is 0 always. It's always true. Nothing about p matters in that equation. If f is equal to 1, you've achieved the minimum number of heterozygotes. The maximum number of heterozygotes, again, is 1. Everybody's a heterozygote, which will occur when 1 equals 2pq times 1 minus f. So I would have had you solve for f in terms of 1 over 2pq and found that value of f in terms of p and q that maximize, it will turn out to be -1 when p is a half, but it will turn out to be either minus p over q or minus q over p, depending on whether p is bigger than a half or less than a half. Does that make sense?
Yeah, it does. I think I just made the,
Again, you
Set
found the
the
absolute
in-
maximum and the absolute minimums of f.
okay. All
I
right.
think maybe that problem was not sufficiently clearly written to have you exactly at what I had in mind. But does this make sense to everybody? Okay. Up next is Sebastian with problem 12. We're going to get through the entire homework today, aren't we?
That was quick. Just give me a second. So can everyone see my screen?
Yep.
Okay, so I
Yeah, why don't you
replicated
just do
this.
snip so that we give everybody a chance? Why don't you just do snip 1?
Okay,
Walk us all the way through snip 1.
so for step 1, I use this formula, which uses the frequency for the first homozygotes and the heterozygotes to obtain the value for P. And from that value for P, I use the frequency of the heterozygotes in this equation to obtain the value for F. And these were my two values, 0.74 and 0.1684.
Looks beautiful to me. Did anyone get anything different than that they would like to discuss? Okay. Mega, why don't you do snip 2?
Can everyone see?
Yep.
So I don't know about my F value. I was just about to ask, but for this one, I did the same thing that Sebastian just did, where I put in the 32 for the A one or the GG, sorry, and then I did 65 for GA to find just the G's or the capital G's, and I got P equals 0.645. And then I plugged that in to solve for F, and I got a negative number.
That's fine. We just proved a second ago the bounds of F are minus P over
I was
Q.
like iffy about it when I got it, but,
Yep.
but I left it. That's what I got.
Because you did it correctly. So, so the interpretation of F, a positive F means you have too few heterozygotes relative to Hardy-Weinberg. A negative F means you have too many. So whenever you look at the frequency of heterozygotes and it is more than you expected under simple Hardy-Weinberg, you ought to be getting a negative F, as you have here. And this is just utterly and completely 100% correct. And the intuition is it's negative because there are too many heads. Did anyone get anything different than this that would like to share it? Okay, Jim, you're up with snip 3.
Okay. So I did a very similar way. For snip 3, which is here in the table, I just took the frequencies for the GG to find the allele frequencies for G at that, and then I just took 1 minus that to get the allele frequency for A.
You bet.
And then when I was solving for F, I kind of just came up with this little equation.
Did one of the harder ways. That was a little bit bit
Sure.
more term to plug into.
Yeah, that's how I tend to do things.
Yeah.
the frequency of the GG minus p squared over p minus p squared. And when I do that for SNP3, I get negative 0.061, which is pretty close to 0.
Yeah. Anybody get a number that was dramatically different than that, or different at all, up to round off? Straightforward. Okay, Julie, SNP4.
Yeah, for SNP4, it's just 2 times 10 plus 35 divided by 200, the total number of alleles. And then, so the frequency is 0.275. And then the frequency of the heterozygotes is 0.122.
Anybody get anything different than that? Like to share? It's absolutely perfect. Any questions so far? Okay, Young Xian, how about the next problem, or at least SNP1 of the next problem?
Okay.
Jack, why don't you do the whole next problem? Isn't it all more of the same? It's just plugging in the formula, a lot of painful little numbers.
Yeah. So, so I looked for how to calculate the chi-square statistics, and it is the sum of the difference between observed and expected value for each observations, and divided by the expected value. So for SNP1, where p equals to 0.74 and the f is 0.26, there's a typo. The chi-square statistic would be, so this is from the question. So this value is, I think, it was the frequency of GG, I guess, minus the frequency of expected GG, which is calculated by multiply p by p, and it is divided by p squared, which is expected value of frequency GG, I guess. Sorry, let me scroll. Yeah, GG. And then this is for the heterozygote. So in the question, the observed frequency of heterozygote was 0.32, and then the expected frequency of heterozygote is 2 times PQ, which is 2 times 0.74 times 0.26, and then it is squared and then divided by the expected value of heterozygotes. And then it is also repeated for the another homozygotes, and then it is all summed up. And then I guess there is a typo here. I mean, there are a lot of typos in this answer, but I got 0.5. And then it is repeated for other SNPs. And
okay. So before we go on, there's actually a subtle error here. So the chi-squared statistic is on counts. So it is the observed count and the expected count.
Okay.
So effectively, every number you have written here needs to be multiplied by 100. So your 0.58 is really 58. Your 0.74 is 74. Your 0.32 is 32. That's something. Your 0.1 is the number 10, and again the expecteds are again 74. So you end up with what you got if we put the n in an appropriate place. Oh, by the way, there's no if you put the n in the appropriate place, you end up with an n squared on the top and an n on the bottom, and this statistic ends up multiplied by 100 versus what you got.
Yeah, I got it.
I have a question about that.
Yep.
So for the 0.74, wasn't that solving for just the like allele G rather than GG?
Yeah, yeah,
So-
exactly.
So if you were doing the chi-squared, would you not have to find like I used the frequency, or not frequency, I guess, the count for like our observed value of GG was 58 minus 55 because it's only GG in the population as opposed to all the Gs, if that makes sense.
Yeah. Your expected is Hardy-Weinberg, right? So here, let me share my screen. Let me see if we can make this clear. I'm not sharing my screen, am I? Come on. Let me try. There we go. So I did it out once. So did I do it for which? So to be clear here, okay. So let's back up to the previous problem. So the observed count, you all can see my screen, right? So the observed counts are 58, 32, and 10. And P is 0.74, Q is 0.6, and the total sample size here is 100 individuals. So I observe 58 individuals. My expected value is P squared, 0.74 squared. That I guess turns out to be 0.5476 something times the number 100 to get 54.76. My genotype count for heterozygotes was 32. That's the number 100 times 2PQ, which is 0.74 times 0.26. And if I've done the math right, that turned out to be 38.48. And we have a Q squared of 0.26, which is Q squared times 0.26, and you get a number of 6.76. So the chi-squared is the observed 58 minus the expected 54.56 quantity squared over the expected, plus the observed 32 minus the expected 38 something quantity squared over the expected, plus the observed 10 minus the expected 6 over the expected, and you end up with 2.84. Does that make sense to everybody? So the expecteds are Hardy-Weinberg, P squared, 2PQ Q squared, P squared, 2PQ Q squared. But the whole way we do this is on counts, not frequencies. And we have an intuition about that, right? If we did it on frequencies, your sample size would never matter. Your significance would never change depending on sample size. But our intuition is this number ought to get bigger as our sample size gets bigger. So our intuition tells us we should be on a count rather than a frequency sort of space. Does that make sense to everybody? Are there questions about this? So when I plug numbers in, I get 2.84 for the first chi-squared. When again, I go P squared, 2PQ Q squared. For the second one, I got quite a bit bigger value. I got 17.59. For the third one, it looks like it's just about perfectly in Hardy-Weinberg, 26, 50, and 34 when I do it. And I get a tiny little thing here of 0.37. In the fourth SNP, I got a value of 1.49. Did anybody, does anyone want to discuss this or show their math or algebra?
Can I ask a question?
Yes, please.
Okay. Well, so I guess even if you use frequencies, though, they're all going to be multiplied by 100 at the end, right?
Yep.
So I guess they're still relatively comparable.
Yep.
but it's just that we should be using them in terms of counts. Or
Yep. And in fact, you even get the intuition in the very last problem why you're going to be able to pull an n out.
Okay.
You're actually going to be able to show that if you'd been in frequency space, you got f squared as your chi-squared value, and the whole chi-squared statistic is n times f squared. And that is going to be like the intuition there, that f squared, yeah, is really fundamentally the chi-squared value for comparison of frequencies. Okay, other questions about this? So the next thing to say,
I had a quick question on it, actually. Maybe you went over this already, but I have always struggled with degrees of freedom.
What's just where we're going on this?
Okay, so why 1?
Okay, so we're going to take for everything we do in our life, we're going to be population geneticists when it comes to estimation of degrees of freedom, and this rule will effectively always give you the right answer. The degrees of freedom is the number of observable classes minus the number of parameters you needed to estimate from your data to create your expectation. So that's really where the term degrees of freedom comes from. It's the number of observations minus the number of ways you used your data to estimate a parameter. That's how much of the data is left to do a test on. That is always going to be your intuition. So the number of observable classes is easy. That's 3. I observe homozygotes, heterozygotes, and another set of homozygotes. 3 observable classes. But what did I need to know from the data to estimate Hardy-Weinberg? I had to calculate P from the data. I had to look at the frequency of these things and get P. I didn't need to calculate Q because Q I just asserted was equal to 1 minus P. But I also needed to count the sample size. I needed to figure out how many observations there were total. If I'd used the number 1,000,000 for observations, I would have got a chi-squared of 1 billion, and it blew up. I had to know the actual sample size. So I needed to calculate P for my data, and I had to calculate my sample size for my data, and that allowed me to write down the expectations. There we go. That is, so my degrees of freedom are 3, but I used up 2 of them, estimating sample size and estimating allele frequency. 1 degree of freedom for Hardy-Weinberg. Hardy-Weinberg has 1 degree of freedom. That 1 degree of freedom can be thought of as F. There's a 2-parameter distribution total. So you got these chi-squared values, 2.84, 17.37, 1.49. And the way a chi-squared test works is, the idea is if the model that gave you the expectation is correct, you expect the chi-squared value to be smallish. The better the fit between the model that gave you the expectations and your observed value, the smaller chi-squared will be. So the bigger the chi-squared value, the worse the model fit, and the more surprised you are by that observation if the model is correct. So we think about the probability of getting a chi-squared value equal to the value we saw or smaller. So for the first one, we have a chi-squared value of 2.84, and we know it is a 1 degree of freedom test. So we go to a chi-squared table, we look up the value 2.84 with 1 degree of freedom. That is the probability of getting a chi-squared value that big or smaller. And you see it's bigger, and you see that value is 0.9. Getting a chi-squared value as big or bigger than 17 is really unusual. That's a 10 to the minus 5th kind of number. The probability of getting a chi-squared A 0.37 is really natural. It's a p-value of 0.5. Of 1.4, it's also sort of natural p-value of 0.2. And most of you probably even have in your head cutoffs for chi-squared, that p less than or equal to 0.5 is probably 3.84, less than or equal to 0.01 is probably 6.63, less than or equal to 10 to the minus third is around 10. Chi-squared of 30 is about genome-wide significance. It's about 1 in a billion-ish, somewhere in that range. So that should be your scale. At like 0.05, you're looking for a number around 0.38, maybe 0.384. A number for p of 0.1, it's 6.6 or so. For 10 to the minus third, it's like 10. And to get real significance, you know, you're really certain 1 in a billion kind of stuff, it's probably around 30. Questions about this?
I do have just one question. I know we've talked about we're working with counts, not frequencies. I tried to approach it by also plugging, like basically doing the frequency at additions and using the F term.
Yeah.
Is that not an appropriate approach? I kind of had some different mathematical errors, so I wasn't really able to get the exact answer. But
Do you want to show? Do you want to show it to us?
Yeah, I'll show you the setup. I know already that a lot of the answers that I had were wrong. I think probably because my math was just there was a lot to calculate, and I plugged probably the wrong things in. But 1 second. All right. So basically it was just, if we look up at the top, this kind of setup. So rather than, so observed minus expected over expected, and then using the frequency terms.
You were just doing the proof for the next thing without the ending.
Yes.
So again, if you multiply all of your observed and all of your expecteds by n, you will absolutely have the correct answer.
Okay, so this is an okay setup. This probably is, again, I had some mathematical errors here, so there's an easier way to do it, but okay, so this is appropriate.
The totally easy way to do it is the frequency, the observed frequency of homozygotes is whatever is given in the table, which you found is going to be p squared 1 minus, like when you successfully found p squared or successfully found p and successfully found f, you knew you could reproduce the value in the table by taking p squared times 1 minus f plus p times f. Or you could have seen it in the table.
Okay, excellent.
Does that make sense?
Yes, yes,
So
it does. Thank you.
that whole thing should give you whatever was in the table, minus p squared. This thing should give you whatever was in the table, minus 2pq. This should give you whatever was in the table, minus q squared. Now we're going to still end up off by a factor of 100, but otherwise is perfectly correct.
Okay.
And in fact, I think you got it right. Like, I think that is, I think mine was 2.8. No, yeah, it's 2.84. Yep.
Oh, okay.
So
Cool.
for your first one, you're off by just literally a factor of 100.
Okay. Oh, so so it is, okay. I think Lenny actually said this earlier, and you could just multiply it by 100. Okay, thank you.
Other questions?
I have one more question, and maybe this is a little bit off topic, but comparing the 4 different SNPs and each of them having different F values, is there any sort of, I guess you have to assume that these are completely like not in linkage to have different F values?
I don't know what the word linkage even means at this point in the class.
Okay. I guess to me, like it's a measure of inbreeding, right? So if you have more of one locus, then wouldn't you also have others nearby? And so these have to be completely independent, right?
Jim, I promise you, you will fully understand the relationship between F and linkage between SNPs before the end of homework 7, I think.
Okay. That's fine.
If you do not, that homework has failed, because the whole way that homework was designed was to give intuition between inbreeding, well, between population structure and its effect on F, and population structure and its effect on LD, and how they are related to one another. And in fact, how one may be a bound on the other in some complicated way. And to give you an intuition that the confounding in your study can be written down as a function of F or F squared or something. So that all of these things are probably related to one another, that your intuition there is deeply correct, and hopefully by the end of homework 7 or something, it won't be intuition, it'll be actually be a little bit of precision in your understanding.
Cool.
Other questions? Okay, do we have a volunteer to do the final proof? Some of you did it right. Come on.
Sure, I'll do it.
Okay. You practically were there with your setup.
It came to me in a moment of lucidity last night, and it was great.
Oh, good.
I think I just had to get tired enough to do the homework.
I won't tell you about my undergraduate friend who insisted in order to do his physics homework, he needed to be stoned.
Too late.
Yeah.
Okay, so number 14.
Forensic here this time.
Yes. So number 14 was showing that the chi-square value, if you can see my mouse, is equal to n f squared. So what I did was I set it up where I set the chi-square value is equal to the sum for n values of the observed minus the expected squared over the expected, which for our allele frequencies, so I plugged in our values, which we know our observed values are going to include an F term, and our expected value is going to be the hypothesis that we've grown familiar with, where A1 is p squared, A1A2 is 2pq, A2 is q squared. So when I started, and just to make it easier for me for the math, I just broke these down to try to reduce everything. I also knew that this was all going to be multiplied by n, because I knew that this was for an n number of values or observations. So I just reduced it down. When you start factoring things out, you can get, and I left the n term out to just make it easier. So you start getting these values for A1A1, A1A2, and A2A2. I also use the rule that my value of Q is equal to 1 minus P, again, so that I would just have 2 terms that I was working with instead of 3. Ignore the middle bit, because then what I did was I took those 3 values together and I knew that I was summing them up. And since you're summing up 3 things that have the common term of n, I just, again, left the n on the outside. And then I also pulled out an f squared, because they all happen to have an f squared factor inside of them. Once you start crossing out those values, you suddenly get, you get the value of 1 in the parenthetical, all multiplied by f squared, all multiplied by n.
Absolutely correct. Just very nice. The only thing special is it's almost a miracle you made it through all that that algebra. We show you when do this. It's not giving me my thing again. That's special. Where is come on. Allow me to share the preview. There it is. So doing the exact same problem, the exact same way Brooke did, chi-squared is equal to n times the observed frequency, but I've written that out in the way that is p squared plus fpq, separated out my f term from the rest. From the expected, which is p squared times n, generalized Hardy-Weinberg times n, but again, I separated out my f, expected, generalized Hardy-Weinberg times n over q squared. But now this is, I've got an np squared, a minus np squared. I've got an n2pq, a minus n2pq. I've got an nq squared, a minus nt squared. So this is just nfpq squared. This is just minus n2fpq squared. This is now nfpq squared. I square everything. I get an n squared and a p squared. Those disappear. And I've gotten an nfq squared. I've gotten an n squared up here, a 2 squared up here, an f squared, a p squared. That becomes nf squared 2pq, nf squared p squared. So it's just, as you said, you can pull out an nf squared and get q squared plus 2pq plus p squared, which is 1. That mess of algebra just becomes much easier to see the answer when you keep the f separate from the beginning. But what you did was 100% correct. It was a bit of a tour de force of getting all that algebra correct. Other questions or comments? That was brilliant, guys. Homework 2 is done. So we will meet next Thursday to answer previous questions about homework 1 or 2 if you've realized you now have questions about homework 1 or 2. I will then field questions about homework 3. Give you little hints, give you little whatevers you need to push you over the limit to get homework 3 done. But hopefully the class will only last a few minutes. Well, it'll last however long it takes for you guys to be satisfied that you are prepared to do homework 3. So I would recommend looking over the homework between now and then and deciding whether you have any questions or concerns. But that was wonderful. You guys did great. And this homework 3 is harder than homework 2. And homework 4 is probably harder than homework 3. Homework 4 may be the second hardest we do in the class. I don't know. Homework 9 is the hardest we will do in the class. So this week, while I know took everybody a long time and was hard, next week will probably be a bit harder. But it will be much more like this week than it was like the first, in the sense that it is all about genetic drift. And it is, although many of the mathematical concepts we previously saw will be important to understanding genetic drift, it'll all be about genetic drift. Questions? All right, come prepared with stuff for Thursday. Otherwise, it'll be a super short class, and I'll see you then.